Hello. So welcome to the last class on NP-complete problems. So today I will discuss some miscellaneous topics related to NP-completeness, NP-hardness and similar issues. So the first topic that I would like to highlight is that so this is this, not all instances of an NP-complete problem are difficult. So by this what I mean is not all. Okay. So by this what I mean is that even if some NP-complete problem is apparently difficult to solve, but that does not mean that all instances of the NP-complete problem are difficult. Okay, so let me give an example, otherwise it's getting a bit vague. Let us consider, for example, the directed Hamiltonian path problem. Okay, by reduction from CNF SAT, we have proved that this is NP-complete, and that proof was quite complicated, but anyway, that's not an issue. Let us consider DAGs, that is, directed acyclic graphs. Okay. It turns out that the Hamiltonian path problem for DAGs, this particular case of graphs, okay, can be solved in polynomial time. Why? Because if a directed acyclic graph contains a Hamiltonian path, then this graph must look like this. And so on. Okay. And there may be other, this is my S, this is my T, and there may be other edges like this, but in the forward direction. Here to here, maybe here to here, here to here, like this. So, if you make a topological sort of your given DAG, it must be of this form, this, and then this, then this, then this, then this, then this. Okay. And there may be other things like this. Okay. So by looking at the topological sort, after you get the topological sorting of this DAG, you find out whether all these edges are there. Okay. First one to second one to third one to fourth one, and so on. If so, the directed acyclic graph has a Hamiltonian path from the source to the target, otherwise not. Okay. So, for DAGs, this directed Hamiltonian path is easy. Okay. So, this is easy for DAGs. Although in general, it's a difficult problem, but for directed acyclic graphs, it's easy. Let me tell something about this also. Longest and shortest paths. Okay, so for the shortest path problem, we have several algorithms like Dijkstra, Bellman-Ford. We also have Floyd-Warshall. There are many such algorithms which solve the shortest path problem in graphs, directed or undirected, in polynomial time. But you recall that all these algorithms fail if they all fail if you allow negative edge weights. Why? So now let us look at the general version of shortest path problems, where edges may be positive, may be negative. Okay, edge weights may be positive, edge weights may be negative. You are allowing negative edges as well. In that setting, so earlier I have talked about longest path with positive edges. So only positive weights. And then I can make a reduction to the general shortest path problem. I already know this is NP-complete. Shortest path definitely is in NP. And if you consider G, vertex at and some edge weight W, and then some S and T, we will map to the same G, W prime, S T. But this time W prime for any edge UV will be just minus W UV. Okay, since now my shortest path instances allow negative edge weights and longest path has positive weights, so I can just make this weights negative. This proves that in presence of negative edge weights, the shortest path is NP-complete. Okay. Moreover, this construction of just flipping the sign of the edge weights makes no distinction between longest and shortest paths, if they both allow positive and negative weights. Okay. So, if you do this construction, a shortest path becomes longest, a longest path becomes shortest. So, this construction is, so longest and shortest, there is no difference if you allow positive and negative weights, both. Okay. But, so, in general, in this setting, shortest path is NP-complete. However, if I restrict the edge weights to positive only, then I see that there are so many easy algorithms, polynomial time algorithms. Okay. That means that although in general shortest paths or longest paths is NP-complete, so these instances containing only positive edge weights, this is polynomial time solver. Okay, because we know so many algorithms. Okay, this is the second example which I introduced in order to illustrate that not all instances are difficult of an NP-complete problem. Anyway, And let us now see, I would say, a couple of examples to show that problems having very similar descriptions as NP-complete problems may be in P. For example, we have seen 3CNF SAT is NP-complete. Today I show that 2CNF SAT is in complexity class P. It has a polynomial time algorithm. Why? This requires a proof. Not so simple. So suppose phi is given formula in the 2 conjunctive normal form. So it is something like this. Literal A1 or B1 and literal A2 or B2 and so on. AK or BK or AL or BL. Okay. So this is 2 literals per clause. So that is why this formula is in the 2 conjunctive normal form. Okay. Now, in order to prove that this is in P, I construct a graph G, a directed graph G, V, E as follows. So V contains, nodes, all variables and their complements. So if there are n variables like x1, x2, x3 up to xn, then this V will consist of 2n nodes labeled x1, x1 bar, x2, x2 bar, x3, x3 bar and so on. Okay. And what are the edges? If A or B is a clause in phi, add the directed edges A complement to B and B complement to A. Okay, I hope I am not making any mistake. Just let me verify. Yes, fine. Okay, so that is the construction. If there are n variables, there will be 2n vertices, and if there are L clauses, there are 2L directed edges for A or B, A complement to B and B complement to A. Okay. Now, why is this graph important? It is important because of the following reason. So, this is the theorem, proposition or whatever you say. Phi is not satisfiable if and only if G contains both an x to x bar and an x bar to x path, both an x to and an x path, directed path, and an x bar to x path, directed path again, for some variable x. x. Okay. Now the proof for this is not so easy, but let me do it anyway. So first the if part. Okay. Suppose that there is a variable x such that the graph contains a directed path from x to x complement and a directed path from x complement to x. Okay. And now take any assignment. Okay. Any truth assignment of the variables. Okay. And this x may be either 0 or 1. So in both cases, I can proceed analogously. So maybe let's assume that x is 1 in this assignment. Then you consider this path, x to x bar. Okay. So here you have x, which is 1. Somewhere down there, you have x complement, which is 0. Okay. Now there is a path like this. So there must be at least one point somewhere where there is a transition from 1 to 0. There must be somewhere like that. So let us call it A or B. Okay. Somewhere there must be there a directed edge. I said this is 1, this is 0. Okay. Now this is a directed path, this is a directed path, eventually ending here. Okay. Some point on the path, this must be a transition of truth value from 1 to 0. If that thing happens, and look at this, how did this A to B edge come in the graph in the very first place? Because there was a clause A or B, or maybe this is symmetric, so B or complementary. Okay, this clause must be there. That is the reason this directed edge came in the graph. So not A, or maybe I use this complement. So let me write it a little bit cleanly. So this is B. So this must be there. That is why this edge is there. Okay. But if A is 1, A complement is 0, B is 0 anyway, so this clause is not satisfied. So this is 0. So this clause is not satisfied and therefore the formula is not satisfied. Okay. So in any truth assignment where x is 1, there is at least one clause that is not satisfied and therefore the formula is not satisfied. And if x is 0, the proof is analogous. Now look at this path, x bar x path. Similar thing will happen somewhere. X bar is 1, this is 0. Somewhere there will be a transition from A to B. This is 1, this is 0. And once again argue as in this case. Okay. So this is one direction. The other direction is a little bit more complicated. But at the same time, this gives an algorithm, polynomial time algorithm, for finding a truth assignment, satisfying truth assignment. Okay. So now what is the thing? Only thing G contains, okay, phi is okay. Let us prove it this way. Yeah. So instead of proving this implies this, I will prove the contraposition. This G does not contain both x bar and x bar x path for any variable x. Okay. Then I will put that phi is satisfied. Okay. So now I start with the premise that G does not contain x complement both and x complement x paths for any variable x. Now what I will do, I will assign truth values to the nodes of the graph following this algorithm. Okay, so long as all nodes in that graph G are not assigned truth values, repeat the following loop. So what is the loop? Pick a literal A such that A may be a variable or its complement such that G does not contain an A to A complement path and such that A is not yet assigned a truth value. Okay. Then you make a traversal in the graph. So assign truth value 1 to all nodes including A itself that are reachable from A. Okay. And not only that, assign truth value 1 to all the nodes that are reachable from A, including A itself, and the truth value 0 to the complements of these variables. Okay. So if there is a path A, B, C, A, D, something like this, then you assign 1, 1, 1, 1 here. Moreover, there is some node A complement, assign 0, B complement 0, C complement 0, D complement 0. Okay. So this is the construction. Okay. I have to show that this makes sense and this assignment is actually well defined, and for this assignment the formula evaluates to true. Okay. So first let me argue that the truth assignment is well defined. So what does it mean, well defined? Okay. So this means that, suppose it is not well defined, which means that there exists a literal B which we want to assign the truth value zero and 1. If that thing happens, then this will be an inconsistent thing. Suppose that there is a literal B to which we want to assign the truth value 0 and 1 simultaneously. Okay. Now this may happen in a single iteration or in multiple iterations. So let us see what is the problem. Single iteration means for a particular choice of A. Okay. So single iteration. Okay. So in this case, I assume that B is not assigned any value earlier. Okay. Now what we have discovered is that like this. Started from A, there is a directed path from A to B. There is also a directed path from A to B complement. If that thing happens, then I will try to assign B equal to 1 and B complement equal to 0, but there is also a directed path to B complement, so I will try to assign B complement equal to 1, B equal to 0. Okay, that's clearly an inconsistency. And let us see why this is not possible. Now you see that okay, this construction is in some sense symmetric. Since there is a A to B complement path, there must be a B to A complement path. Okay. Because of this construction. Just look at this construction. A complement to B, B complement to A. So this is kind of symmetric. So if there is a to B path, there must be a B complement to A complement path. Okay. So you have an AB path, you have A B complement path. This implies there exists B complement A complement paths and B A complement paths. So now if I look at this path and this path, they together give me a complement paths. Okay. But by construction, I assume that a complement path does not exist, does not contain a complement path. Okay. So that proves that this case cannot happen. Okay. But it is also possible, I have to rule this out. B was assigned earlier. Okay, and now I once again have discovered something like this. Assigned earlier, so now I have discovered B and trying to assign it the value 1. If it is assigned earlier the value 1, there is no inconsistency. So I assume that B is assigned 0 earlier. Okay. So now I am trying to assign 1. Earlier it was assigned the value 0. So that's a clear inconsistency. Let us see why this is not possible. Okay, so in an early iteration, B was assigned 0. That is, B complement was assigned 1 earlier. Okay. Now, since A to B is a path, again by symmetry, there exists a B complement, A complement path in the graph. Okay. Now, from wherever we have started, maybe from C or somewhere, we reached B complement, set it to 1, but we did not assign any truth value to A. Why? C to B complement there is a path, and B complement to A complement there is a path. So I didn't set A complement equal to 1 or A equal to 0. Okay, why? Okay, this is once again invalid by this construction. A is not yet assigned a truth value. Okay. If B bar was reachable, A bar was reachable, therefore A bar and A both should have an assignment. In this case cannot happen. A is not yet assigned a truth value. Okay. Okay, so this assignment is after all consistent. We never try to do a bad thing. So the final thing that remains to show is that, so now I have truth values for all the variables and their complements. So this truth assignment satisfies 5, the input formula. Why? Now, this is the most important observation here. The construction suggests that we have never done something like this. 1 and this is 0. Whenever there is a directed edge, whoever assigns 1, this will also assign 1 here. Okay. So no such edges. Okay. This is very important thing. There is no edge such that there is a directed link from A to B. This is 1, this is 0. Okay. So now take any clause A or B in phi. Okay. Take any clause. Then what do I know? There is a directed edge from A complement to B and a directed edge from B complement to A. Okay. Now if A is 0, this implies A complement is 1. Okay. And again, because this cannot be 0, so this must also be 1. So, if this is 0, this must be 1. So, this is satisfied. And if B is 0, B complement is 1. And since this case is never possible, this must be 1. Okay. So, if B is 0, A must be 1. If A is 0, B must be 1. So, in either case, A or B is satisfied. So, each clause is satisfied in phi. Okay. So, that's the end of the proof and the construction. A little bit complicated, but interesting, because 3 CNF satisfiability is NP-complete, whereas 2 CNF satisfiability is in P. Okay, this is yet another, I would say, similar problem. So far we have been considering only CNF satisfiability. What about DNF's satisfiability? So what is disjunctive normal form? This is basically sum of products. Okay, a disjunction of a conjunctions. Okay, that is why I call disjunctive normal form. Anyway, whatever it is. Now, so using this Boolean logic expression, I can write such an expression, such a formula in this form. Product 1, product 2, product 3, formula in disjunctive normal form is of this form, PL for sum L. Now, since this is a sum or disjunction like this, it suffices for this formula to be satisfiable that at least one of these products are or is satisfied. Okay, so if this is phi, so phi is satisfiable if and only if at least one pi evaluates to 1. And when does a product evaluate to 1? So let's say we have literals and a product evaluates to 1 if and only if it does not contain both a variable x and its complement. So that's an easy check. Okay, look at each of this product and find out whether this case occurs. If not, you immediately say phi is satisfiable. Otherwise, if it happens everywhere, then you say the phi formula is not satisfiable. So it's just looking at the formula, I can easily derive whether phi is satisfiable or not. So disjunctive normal form can be checked. I mean satisfiability in the disjunctive normal form can be checked in polynomial time fairly efficiently. Okay. Okay. And okay. There is another problem which I introduced earlier but never talked about. That is the Eulerian tool problem. We have seen that this problem is in NP, but we have not talked anything about whether it is also in P. In fact, this is in P. Okay. Now, okay, maybe. Eulerian in 1873 proved this. G is Eulerian, that is contains an Eulerian tool if and only if G is connected and every vertex of G has event degree. It's a fairly straightforward thing to check whether the graph is connected. Use BFS, DFS, some traversal, and by looking at the representation of the graph, you can just check whether every vertex has event degree. Okay. I will not give a proof of this, little bit involved. For example, if you are interested in a proof, it's available many places. For example, you can look at the textbook on graph theory by Douglas West. Okay. So the decision problem can be easily solved by looking at the graph and making a traversal in it. Now, that's also important and interesting. So, if graph is Eulerian, then Eulerian, how to compute such a tour? So, how to, suppose this is satisfied, so you know the G is Eulerian, so how to compute an Eulerian tour? So I mentioned an algorithm, I will explain the algorithm, but its proof of correctness I am not covering. So this is known Fluidist algorithm. This algorithm works as follows. So start at an arbitrary vertex and let us call it V1. So suppose V1, V2 up to Vi on a tour are already generated for some I greater than equal to 1. Okay. Then the question is how to generate the next vertex on the Eulerian to Vi plus 1. Okay. So look at the neighbors, or I would say the remaining neighbors of Vi. Okay. If only one such neighbor exists, pick that as Vi plus 1. Okay. If many neighbors, pick any Vi plus 1, any such neighbor as Vi plus 1, provided that removing the edge Vi plus 1 does not disconnect the graph. And this is where you need some proof. If a graph is Eulerian, you will always find a neighbor such that the removal of the edge Vi plus 1 will not disconnect the graph. Okay. Okay, so we have chosen Vi plus 1, then just two more things to do. Actually remove the edge Vi plus 1. Okay. Moreover, if Vi has no more neighbors, delete Vi. Okay. That's a simple-minded algorithm called Fluidist algorithm, and this choice requires a proof. Okay. So I am not going to the details. Okay. Okay. So that's again a problem which is NP. Okay. So now let me just end up this session and this chapter on NP-Completeness by mentioning something which I promised to tell earlier. All NP-hard problems. Okay. I should better write it this way. Not all are NP-complete. So there are NP-hard problems outside the NP class. Okay. So I will give you an example to illustrate this. The halting problem is NP-hard. So of course you have seen a version of the halting problem in connection with Turing machines. Now let me just rephrase this halting problem in terms of C programs maybe. Okay. So this takes two things, a C program let's say Q and an input I for Q. So these are the two inputs of the halting problem. Okay. Now decide whether Q halts on input I. Okay. So this is the halting problem in this context. Essentially it is the same as the halting problem for Turing machines. Okay. And you can propose a diagonalization argument as we have done there. Such a diagonalization argument proves that this halting problem, again let me call it HP, is unsolvable. This is very important. It is unsolvable. Whereas NP consists of problems which are solvable in non-deterministic polynomial time. They are all solvable problems. If you want to solve them deterministically, it may so happen if P is not equal to NP that you take exponential amount of time, but still these are all solvable problems. Okay. So NP contains solvable problems. Therefore, the halting problem is definitely not in NP. Okay. So I have to show that the halting problem is NP-hard. Then I am done. Okay. So next claim is the halting problem is NP-hard. Okay. So maybe I will make a reduction from CNF set to halting problem. Okay. So given a formula phi, maybe in CNF this form or just set doesn't matter. I will write a program P and I will input this formula phi to this program. Okay. Such that this is satisfiable if and only if P halts on this input phi. Okay. So how do I generate this program P? So count the number n, let's say, variables n5. Okay, then you just write a function to evaluate phi on or for any given truth assignment of the variables. Then write a loop maybe from I equal to 0 to power n minus 1. And these are all n-bit strings and can be naturally associated with truth assignments 0, 0, 0, 0, 0 to 1, 1, 1, 1, 1. If phi evaluates to true on this assignment I, exit 0. Okay, so this is the loop. And so if phi evaluates, exit 0, program halts. Otherwise, after the loop, we just say while 1. Okay. So if phi never evaluates to true on any value of I in the desired range, you simply come out and enter an infinite loop. Okay. So what is important to note here is that, so this is satisfied, right? So if phi evaluates to true, if it is satisfiable, it will be decided this place somewhere for some value of I, and so the program halts. And if it does not if it is not satisfiable, then this program will enter this while loop. Okay. So he halts on phi if and only if phi is satisfiable. Okay. Also, you convince yourself this is a polynomial time reduction. Okay. You are actually not running this program P on phi. Okay. Because this loop takes 2 power n time. It is not a polynomial in n. Maybe not polynomial in the input size. Okay. But it's not your duty to run this program P on phi. Okay. It suffices that you generate this program and this input. This input is just copied from here. So it suffices to write this code. That can be done in polynomial time in the input size. Okay. So then what is the final conclusion? There is at least one problem which is NP hard but cannot be in NP because it's not even satisfiable, solvable. Okay. So to sum up, I have the following complexity classes. Something like this, and a subclass like this. So this is my NP, this is my P, and there is also some. So this is this class of all NP hard problems, and this part which NP hard intersects with NP. So this part is the set of all NP complete problems. Okay. Now, of course, it is not known whether P is equal to NP. If P is equal to NP, then every problem is NP complete also. So, but if P is not equal to NP, then all these containments are proper. Okay. So if Okay. Yeah, because if any, and of course, this must be disjoint from this in this case, because if any NP-complete problem can be solved in polynomial time, and we have seen that any problem in NP can be solved in polynomial time. So, this must be disjoint from this. But anyway, so this is just the beginning of the complexity classes. So, you will learn more about complexity classes in your theory of computation course. So, fine. So, I believe this is all that I wanted to say about NP-completeness and some related issues. Our next topic will be how we can solve difficult problems. Okay. So, we will see several things like approximation algorithms, randomized algorithms, branch and bound algorithms, which can be used to solve certain instances of NP-complete problems or solve some NP-complete problems approximately, not exactly. Okay. So, fine. So, I think I am just approaching 1 hour. So, let me stop. See you again.